Hi everyone, in this video we'll be talking about circular motion. There's not going to be a whole lot of problems or examples. In fact, they're not going to do any examples in this video at least. But it's really just going to be a derivation that I would like you to see. It's standard out of a physics textbook and it's not all that difficult, so just watch it at least once and understand the results and take it to heart. So, when working in radians, I'd like you to know that the sine of theta is approximately equal to theta, as long as theta is small. Objects moving in a circle accelerate because the direction of their velocity changes. So velocity consists of both a magnitude and direction. It's a vector quantity. And so if the velocity changes, either its magnitude or direction changes, then it must be accelerating. And so we'll see that we have an acceleration that isn't associated with a change in speed. This acceleration is called the centripetal acceleration. Its direction is inward toward the center of the circle, and its magnitude is a equals v squared over r. And I've written it here as a cent for centripetal. An alternative form of the centripetal acceleration is a equals omega squared r, where omega is the angular velocity, and omega is 2 pi divided by a capital T, or omega equals v over r. I'll show you what both of those equations mean when we're ready to define those variables. So let's talk about radians and approximation. In your trigonometry class, you probably encountered radians at least briefly, and so you should know why. Why are degrees not good? I'll tell you that degrees are fine for a lot of applications, but in certain applications you really want to use radians. An angle in radians is defined to be the ratio of the subtended arc length divided by the radius of the circle. So here's S, which I'll call, which is the arc length, okay? So it's in green, and it's just this portion of the circle. I can erase the circle, and you can maybe see it a little bit better. So here's just the arc length involved. The circle is radius r. I've written drawn two radii here. And theta in radians is defined to be s divided by r, the arc length divided by the radius. Okay, so why radians? Well, the entire reason that we use radians in some applications instead of degrees is essentially that when using radians for small angles theta, sine theta is approximately equal to theta. So for example, I'm going to calculate the sine of 0.001 radians. I know I ask you to pause the video a lot and to work on problems yourself, but this time I really, really want you to do it. So pause the video, get out your calculator, make sure it's in radian mode, okay? You want to make sure that it's in radians, and then take the sine of 0.001. Take the sine of any other small quantity. So you might take the sine of 0.0001 or sine of 0.0005 or something like that. Okay, so do that as many times as you want to convince yourself of this. And when I do it, here's what I get. My calculator tells me that the sine of 0.001 is 0.00099999833. And then there's a bunch of threes that follow after that. And this is, in fact, not going to be a rational number. It's going to be a bunch of threes for a while, and then it will change to some other numbers. But the point is that it's 0.000999999. 0.0009999 is really close to 0.001. Go ahead and take the difference between those, maybe take the percent difference between them, but you should see that they're very, very close to each other. Don't be fooled by this extra zero here, because 999 is going to round up very easily to 1 in this digit. Okay, so please, I hope that convinces you that sine of theta is approximately equal to theta. I've chosen a small theta. Choose a smaller theta, and you may actually overflow your calculator in the sense that it won't give you these extra digits. So find a nice calculator that will give you a lot of digits. Wolfram Alpha is a good choice for that. Pick some small angles and see that the sine of theta is very close to theta when we pick, when we're working in radians and when theta is very small. Try it in degrees and you'll see it doesn't work. I really would like you to take that point to home because, again, it's the entire reason that we use radians, basically, at least for the sake of this class. All right, let's characterize uniform circular motion. For many problems in Newton's laws, we will be concerned with objects that move in a circle at a constant speed. So I've drawn two representative times. Here it is displaced to the right, and it's traveling upward along the circle, tangential to the circle, and then at some later time it's up over here and it's traveling up and to the left, again still tangential to the circle. But the point is that it's going to continue traveling around the circle at a constant speed, but its direction is going to change. So although the speed is constant, the velocity is not constant because the object's direction of motion changes. Since the velocity is not constant, the object must be accelerating. So I want you to, if you've up to this point considered that acceleration is associated with change in speed, I want you to get that out of your mind. There is an acceleration involved here. We wish to determine the magnitude and direction of this acceleration. So let's derive it. Imagine that an object is traversing a circle of radius r at speed v. At some instant in time, it happens to be displaced to the right, as shown below. This is almost identical to the previous page. I'm just cleaned up the figure a little bit, and we only draw the object here traveling upward. It could be traveling clockwise just as easily, but we'll work with counterclockwise. We will determine the object's instantaneous acceleration by deriving its velocity a short time before and a short time after this moment. Call this short time delta t. So basically what we'll see on the next page is that a time interval of delta t before the object was somewhere down here and traveling up and to the right. A time interval of delta t later, the object is up here and traveling up and to the left. So we'll analyze that motion. Since the object travels at constant speed v, it subtends an arc length of delta s equals v times delta t in both the time delta t before and after the moment in question. V is the speed of motion tangential to the circle, and so it's also the rate at which it subtends a new arc length over change in time. So yeah, it's it will subtend an arc length of delta s and time delta t if it's traveling at speed v. Okay, the associated angle in radians is therefore delta theta is equal to delta s divided by r. That's the definition of theta. And that's v delta t divided by r, which is v over r times delta t. This is just rewriting this in a few different ways. So here's a sketch of this situation. Here's delta s in the delta t after the object was displaced horizontally. And here's the same delta s in the delta t before the object was displaced horizontally. So both of these are equal to v delta t. The initial velocity at the start of this time interval was v naught, and the magnitude of v naught is v, but it's traveling up and to the right. And the final velocity still has magnitude v. Remember, the speed is constant, and it's traveling up and to the left. It's gone through an angle of delta theta after delta t and an angle of delta theta before, in the time interval delta t before it reached this displacement. Okay, using a little geometry, it can be shown that both v final and v initial make angle delta theta with vertical. I'll leave that step for you to derive. It's not especially difficult, it's just that this video already has enough information in it. So what I'm saying is that if this here is delta theta, then we also know that relative to vertical, this is also delta theta. And I hope that that's at least plausible to you. You may not immediately believe it, but do a little bit of geometry and you should be able to see it without too much trouble. And then likewise, down here, this is also delta theta. Okay. So this allows us to do some vector decomposition on both v final and v initial. Remember that they both have the same magnitude of v. So we'll just write them as v. And this should by now look pretty familiar to you. This is very much this is a very similar notation to what we used when we were doing vector addition of velocities in 2 dimensions. So the x component of v final is this component, which is opposite our angle delta theta. And so is it positive or negative? Negative, it's in the negative x direction. Magnitude of the vector is v. Sine or cosine, it's opposite, and so it's going to be the sine of delta theta. V final y, let me actually just draw that explicitly. There we go. That's adjacent to theta. Positive or negative, it's in the positive y direction. Sorry, let's do this in black. Positive, magnitude of the vector, v. Sine or cosine, well, it's adjacent to theta, so it's cosine of delta theta. All right. Do the same thing over here. Now that I've done this one, you may want to pause the video, see if you can do it yourself. V naught x, is it positive or negative? Well, I see that it has a component in the x direction, and so it'll be positive. Magnitude of the vector, v. Sine or cosine, it's opposite the angle in question, and so it'll be sine. And that's delta theta. Sine of delta theta. Okay. And then finally, v naught y. What's the, is it positive or negative? Well, I see it as a positive y component, so positive. Magnitude of the vector, v. And sine or cosine. Well, shouldn't surprise you. It's adjacent to theta. There's the y component. And so, according to SOHCAHTOA, we use cosine of delta theta. Okay. So we've broken it up into components. And average acceleration is a average, I need the vector sign over it, equals v final minus v initial vectors divided by t final minus t initial. And so for the numerator, we're going to find, component by component, we're going to find the average acceleration, component by component. V final x minus v initial x. I've put both of the vectors together and then just said take the x component of both of these. But you can take the x components individually. And v final x is negative v sine delta theta. And then we subtract v initial x, and so it's minus v sine delta theta, which is negative 2 v sine delta theta. Furthermore, for the y component, again, this is v final y, this guy, minus v naught y, this guy, and we get positive v cosine delta theta minus v cosine delta theta. And you should always be happy when you see, well, maybe not always, maybe you've made a mistake sometimes. I've had situations like that. But in this case, there's no mistake, it's 0. Okay, so this represents the numerator of this expression, or at least the component by component, the numerator of the average acceleration vector. Meanwhile, the denominator is the time interval from delta t before to delta t after, or to delta t total. So one way to think about it is that t initial is negative delta t, t final is delta t, and so you get delta t minus negative delta t, and you get 2 delta t. Okay, but putting this all together, we find that the x component is, in the numerator, we had negative 2 v sine delta theta divided by 2 delta t, which is, those 2's are going to cancel, and we'll get negative v times the sine of delta theta divided by delta t. For the y component, for the numerator we had 0, for the denominator we again have 2 delta t, but 0 divided by anything is still 0, and so we're done with the y component. It's not accelerating in the y direction at that time. Okay, so here's our exact expression. Here's what could be our endpoint, except we can already see that the acceleration is, well, let's talk about this first. We can already see that the acceleration is directly to the left. I didn't draw my coordinate axes. I did. I drew them back here. Okay, so here's our coordinate axes. The point is that the object is displaced to the right and it accelerates to the left. The x component of the acceleration is negative, and so it's accelerating to the left. So you can already see that the acceleration is directly to the left, toward the center of the circle. We can improve our expression for the magnitude of a by assuming that delta t is very small, allowing us to use our sine of theta as approximately equal to theta approximation. So, I don't really want to do the vector a, I want to do the magnitude of it. So, the acceleration is just the x component of the acceleration. And it's negative v times the sine of delta theta over delta t. Well, sine of delta theta, let me run back here. Delta theta we had was v over r times delta t. Okay, so they're related in that way. So sine of v over r times delta t divided by delta t. And now we can use our sine of theta is approximately equal to theta approximation. As long as delta t is very small, v is finite, r is finite, so we'll just consider a very short time. We'll consider the acceleration from 0.001 seconds before to 0.001 seconds after the object is displaced to the right. And we get negative v times v over r times delta t, as long as we're working in radians. Divided by delta t, well, these delta t's are going to cancel, and we can join these v's up together. And so we'll get v squared over r. The negative sign reflects the fact that this is just the acceleration in the x direction, and so it's the horizontal component of the acceleration. It's saying that it's accelerating to the left when it's displaced to the right. So the smaller we make delta t, the smaller delta theta is, and the better this approximation holds. In fact, the expression is exact for instantaneous acceleration. This is just saying that if we have an arbitrarily small angle, then the sine of that angle gets arbitrarily small to gets arbitrarily close to the angle that we're plugging in. Okay. Centripetal acceleration. By considering the circular symmetry of the problem, we can deduce that the acceleration is always opposite the object's displacement relative to the center of the circle. In other words, the acceleration is always inward towards the center of the circle. It is not outward. So, it was displaced to the right, and it accelerated to the left. It could be displaced upwards, and it will accelerate downward. It could be displaced to the left, and it'll accelerate to the right. So this is what this looks like, is that the particle is at all times, these blue arrows represent v, the velocity vector, and so at all times it's moving tangential to the circle, but at all times it's accelerating in towards the center of the circle. When it's displaced to the right, it accelerates to the left. When it's displaced up here, it accelerates down. When it's displaced down here, it accelerates up. When it's displaced somewhere to the left, it accelerates to the right. and so on. So you can see that as long as it's moving at a constant speed, the acceleration is constant in magnitude, but the direction is always inward towards the center of the circle. We therefore call this the centripetal acceleration from the Latin roots. Centrum for center, so you should know centrum means center, that I think is obvious enough. And petere meaning seeking. That's probably not so obvious to you. Petere is where we get the root of certain words like impetus, petulant, I think compete, words like that. Okay, so petere means seeking. So this is the center seeking acceleration, if you happen to know Latin. We sometimes distinguish the centripetal acceleration from other accelerations by giving it the subscript cent. Regarding Latin, back in the 1700s when they were first discovering all of this stuff, they really liked the ancient Romans. They thought that they were really brilliant and were basically trying to rediscover everything that the Romans had figured out. You know, that was what they took science to be, was let's figure out what the old people who were much cleverer than us were able to come up with. And so they wrote all of their papers in Latin to make them seem a little bit more important. That died out sometime around the 19th century when they said, hey, wait a second, I think we're doing better than the Romans ever did. So that's why all of this stuff is based on Latin roots, and why you need to learn Latin or sometimes even Greek in order to do a little bit of basic physics. But if you were working in the 18th century, if you're working in the 1700s, and you saw centripetal acceleration, you would probably know Latin and you'd say, oh, of course, it's the center-seeking acceleration. So I don't know why that stuck with us up to this point. Okay, so A centripetal is equal to v squared over r. I've dropped the negative sign to just say, okay, its magnitude is v squared over r, and the direction is inward towards the center of the circle. Those are the two facts that I would primarily like you to learn from this video. But let's take this opportunity to define the angular velocity. So while we're talking about circular motion, let's define the angular velocity to be the rate at which the object sweeps at an angle. Omega, this is not a W. I know my handwriting isn't very good, but this is a Greek letter omega, which you would write something like that. It's the last letter of the Greek alphabet. Omega is defined to be, and that's what the little colon next to the equal sign means. It means it's defined to be delta theta divided by delta t. I'd like you to compare that with v equals delta x over delta t. Or theta final minus theta initial divided by t final minus t initial, where theta is typically given in radians. We don't often encounter omega in degrees per second. So omega will be in radians per second because theta is in radians. So we'll get radians divided by seconds. Oftentimes we are told the time capital T it takes for the object to complete one entire revolution. And there are 2 pi radians in a circle, which is 1 revolution. And so we'll have omega equals 2 pi divided by t. So the circumference of the circle is 2 pi times the radius, and that's the entire arc length. And you divide that by r to get the angle, and so there's 2 pi radians in an entire circle. And so basically omega is telling you how long does it, or let's go with t. T tells you how long does it take to complete 2 pi radians to go through one entire revolution, or 2 pi radians, and omega says take that 2 pi and divide it by t. So this is for an object with constant angular velocity. If angular velocity is not constant, you can't use this. You'll always see constant angular velocity. No, I take that back. You won't always see constant angular velocity in this class. We'll have some angular acceleration later on. And we can also relate omega to v and r. The circumference of the circle is 2 pi r, so it must take t equals 2 pi r divided by v, that's the circumference divided by the speed, to complete one revolution. This gives omega equals, I'll remind you, 2 pi divided by t, which now will be 2 pi divided by 2 pi r divided by v, and we have a denominator, or a fraction within our denominator, And so that means we can invert the fraction and multiply. I'll let you take your time to figure it out yourself, but you'll get v over r, okay? Omega equals v over r. And from this, it follows that a centripetal is v squared divided by r. We already found that. But what I'll do is I'll use this top equation to determine that v is equal to r times omega. And I'll plug that in down here. R times omega, square it, divided by r squared, omega squared, divided by r. And one of these r's will cancel. And typically we write it as omega squared times r, not r omega squared. But yeah, these last two equations are perfectly valid. Omega equals v over r, and a equals omega squared r for centripetal acceleration. Again, the direction is still inward towards the center of the circle, never outwards. If you think it's outwards, it's because you're using a bad coordinate system. And I'll have a lot to say about that when we cover Newton's first law of motion. So let's wrap things up. These derivations are a little long, but well within your grasp. I don't think I've done anything in this video that is especially difficult. It just, maybe it was a little bit time consuming. The new piece of information is that the sine of theta is approximately equal to theta when you're working in radians. So please keep that in mind. I won't expect you to reproduce them, but I will expect you to remember the results, especially for when we cover Newton's laws. And so here's the results all in one place. A equals v squared over r. That's how you'll usually remember it. But omega is defined to be delta theta divided by delta t. We can calculate if omega is a constant angular velocity. Omega equals 2 pi divided by t. And a centripetal, or a, is equal to omega squared times r. And then finally, for the, I'll say this for like the 8th time, centripetal acceleration points inward towards the center of the circle. If you followed this derivation, you must accept that the acceleration points inward, never outward. So that's it for this video, and that actually does it for the entire first portion of the course. So you should be ready for your first exam, which is probably coming up soon, go back and watch the videos over again from the start and see how much you can absorb from them, and hopefully you'll be ready for the exam when the time comes. So I'll try and get a review video up, but other than that, good luck on your test, and I will see you in class. Bye bye.